Welcome to section 4.6, Logarithmic and Exponential Equations. So previously, we solved logarithmic equations by changing a logarithmic expression to an exponential expression. So recall the definition of a logarithm states that y equals log base a of x if and only if x equals a to the power y, where a is greater than 0 and a does not equal 1. For example, if we want to solve log base 2 of 1 minus 2x equals 3, we start by writing the logarithmic equation as the equivalent exponential equation, 2 to the power 3 equals 1 minus 2x, which then can be solved for x, keeping in mind that the domain of the original function, 1 minus 2x, is greater than 0, or x is less than 1/2. And then we can verify that the solution is x equals negative 7 over 2 by substituting that into our equation. Note that not all logarithmic equations can be solved by writing the logarithmic equation as an exponential equation. So there is another property we will often use to solve logarithmic equations, and this property is a result of the fact that the logarithmic function is 1-to-1. And this property states that if log base a of m equals log base a of n, then m equals n, where m, n, and a are positive and a does not equal 1. So taking these properties, we're now going to solve some logarithmic equations. So here we're asked to solve 6 times log base 2 of x equals log base 2 of 64. We're first going to find the domain, then we'll solve the equation, and then we'll check to verify that our solution is correct. So our domain, we know here that x has to be greater than 0. It's a requirement. So taking our equation, 6 times log base 2 of x equals log base 2 of 64. We are going to write our log as a single logarithm with no factors being multiplied. So we'll move the 6 to the power location. So that'll be log base 2 of x to the 6 equals log base 2 of 64. So now that we have single logs, we can now drop the logs. And so we'll have x to the 6 equals 64. Okay. Now I can take the 6th root of both sides. Okay. And so x then will equal plus or minus 2. Since we know that the domain has to be x is greater than 0, we can discard negative 2. So negative 2 is actually an extraneous solution. And so we know then that x equals 2. And we can substitute this back to determine if it is a correct solution. So we'll have log base 2 of 2 to the 6 and 2 to the 6th power equals 64. And so log base 2 of 64 equals log base 2 of 64. And so we know that's correct. All right, let's do the next one. So we have log base 20 of x plus 9 plus log base 20 of x plus 1 equals 1. Okay, so the first thing we want to do is find our domain. So we have two expressions here that we need to check. So we have x plus 9 has to be greater than 0, and x plus 1 has to be greater than 0. So x is greater than negative 9, and x is greater than negative 1. Okay? Well, we know that it has to be true for both log expressions. So x is going to have to be greater than negative 1 because any values less than -1 would make our second log undefined. So our domain is going to be x is greater than -1. So let's take our expression, or equation, sorry, and let's write that out. So we have two logs that are being added together, so we know we can use one of the properties to combine them into one log. So let's do that. So we have the log base 20 equal x plus 9 times x plus 1. Okay, so now we have a single log. So we can now rewrite this log statement as an exponential statement. So we'll have x plus 9 times x plus 1 equals 20 to the first power, or just 20. We have two binomials being multiplied together, so I can use FOIL in order to combine them. So I'll have x squared plus 10x plus 9 equals 20. So I have an x squared, so I know I'm going to be working with something relating to quadratics, so let's set this equal to 0. So x squared plus 10x minus 11, because I'll subtract 20 to the other side. So now let's factor this quadratic, because it is factorable. So I'll have x plus 11 and x minus 1. So if I set both of these factors equal to 0, I'll get x equals -11 and x equals 1. Okay? But remember, x has to be greater than -1. So x equals 1 would be our solution, because -11 would be our extraneous solution, so we would need to discard it. So let's check to make sure that x equals 1 is the solution to this equation. So we're going to substitute 1 back into our equation. So that's 1 plus 9. And then we have log base 20 of 1 plus 1, and we want it to equal 1. So we have log base 20 of 10 plus log base 20 of 2 equals 1. Since we're adding, we can multiply by taking log base 20 of 10 times 2 equals 1. 10 times 2 is 20, so we'll have log base 20 of 20, which equals 1, which is one of our properties. Okay. So caution, a negative solution is not automatically extraneous. We must determine whether the potential solution causes the argument of any logarithmic expression in the equation to be negative or 0. Okay. So here we're dealing with natural logs in our equation, and we have the natural log x equals the natural log x plus 15 minus the natural log of x minus 1. So to find the domain, we're going to set each part of the log to where our value is greater than, not 10, 0. That should be the 0. Okay. So this will allow us to identify the domain of our equation. So we'll have x is greater than -15 and x is greater than 1. Okay, so we now want to identify the domain. So the first natural log, x has to be greater than 0. The second one, x has to be greater than -15. And the third one, x has to be greater than 1. So we're going to use x has to be greater than 1 because the other two will disqualify the first one. So x has to be greater than 1 because then the first natural log will exist, the second natural log will also exist, and then the third obviously would exist. Alrighty, so let's solve this. So we have the natural log x equals the natural log x plus 15 minus the natural log of x minus 1. Okay, So on the right-hand side, we're subtracting two natural logs, so we can use the property to combine that into a single log by dividing. So we'll have the natural log of x equals the natural log of x plus 15 divided by x minus 1. So now that we have natural log on both sides, we can drop the natural logs and set x equals x plus 15 or x minus 1 equal to each other. And so now we can solve for x. So to get x minus 1 out of the denominator, we're going to multiply both sides by x minus 1. Then we're going to distribute the x. So that would be x squared minus x on the left-hand side. Then we're going to move all terms to the left-hand side. Now we have a quadratic, which is factorable. Now we can set both factors equal to 0. And we'll get x equals negative 3 and x equals, that shouldn't be because it's a negative 15. Good catch. That should be negative 5. So that would be a positive 5. Yeah, okay, now that works. Okay, so negative 3 and 5. All right, so we know our domain has to be greater than 1. Okay, so x has to be greater than 1. And so we know then that x equals 5 is going to be our solution. And we can then check that by substituting 5 into the original equation. And then we'll simplify using the properties to determine whether it makes the statement true. So we'll have the natural log 5 equals the natural log of 20 minus the natural log of 4. Since we are subtracting, we can divide 20 by 4, and we get the natural log of 5 equals the natural log of 5, which is true. Therefore, we know 5 is a solution to this equation. Caution: in using properties of logarithms to solve logarithmic equations, we want to avoid using the property log base a of x to the r equals r times log base a of x, where r is even. To see why, consider the following. If we have log base 3 of x squared equals 4, the domain is going to be all real numbers except for when x equals 0. Okay. So if we look at our first method here, we can rewrite this as an exponential statement where we'll have x squared equals 3 to the 4th. So then we'll have x squared equals 81, which we can then take the square root of both sides, which then gives us negative 9 and 9 as our solutions. For method 2, we could move the power 2 to the front, giving us 2 times log base 3 of x equals 4. This will allow us to solve for x by first dividing both sides by 2, which will give us log base 3 of x equals 2, where x is going to then equal 3 squared, which then x then equals 9. Okay, so which method then is correct? It would be method number 1. Okay, method number 2 is not correct because it doesn't find the solution negative 9 because the domain of the variable was restricted. Okay, So we automatically then assumed that our power has to be positive when we moved our power to the front location of our log. So when we are dealing with equations that have an even power, we want to make sure that we avoid using the property that allows us to move the power to the front. Okay, so the following guidelines will be helpful when solving logarithmic equations. So we want to use the properties of logarithms to write the equation in one of the following forms. So we want a log base A expression equals constant, or log base A expression 1 equals log base A expression 2. If the equation has the form log base A expression constant, we then are going to change that that equation to an exponential form to remove the log and then solve for the variable. If the equation has the form log base A expression equals log base A expression, then we can drop the logs and set the two expressions equal to each other and solve for the variable. Once we have solved for the variable, we then want to check our solutions and remember to consider the domain of any logarithmic expression in the equation. Okay. Objective 2. Solve exponential equations. So in the previous sections, we've solved exponential equations algebraically by writing each side of the equation as a single exponential expression with the same base. So we can recall that if a to the u equals a to the v, a to the power v, then u equals v, where a is greater than 0 and it does not equal 1. For example, 4 to the power 2x plus 1 equals 16. So we can rewrite 16 with a base of 4, which would get us 4 squared. Because we now have the same base, we can drop the base and set the powers equal to each other. And then we would then solve for x. So we would subtract 1 on both sides and then divide by 2, giving us a solution x equals 1/2. So this process worked for this equation, but not all exponential equations can be expressed so that each side of the equation has the same base as this following example. So 3x equals 12 is our first one. And you see that we cannot write 12 with a base of 3. So since we can't do that, we can rewrite this exponential equation as a logarithm equation. So we'll get x equals the log base 3 of 12. Since we have a different base than a base of 10 or a base of e, we can use the change of base to help us. So we have natural log 12 divided by natural log of 3. And yes, we can also use the common log as well. And so we would then substitute this into our calculator to get an approximated value. Another process that you can take, we have 3 to the x equals 12. We know that both sides of our equation, we are unable to get the same base. So we can then apply the natural log right away to both sides of our equation. We can then move our power to the front and then divide both sides by the natural log of 3, which we can then substitute into our calculator to get an approximated value. But this allows us to find the expression that represents x. All right. Both methods work in solving exponential equations. So let's do a similar one. We have 5 times 4x, not 4x, 4 to the power x, I have to say that correctly. 5 times 4 to the power x equals 7. So 5 times 4x, 4 to the power x, I said it again. I shall correct myself. All right, so here we have on the left-hand side 4 to the power x being multiplied by a factor. So in order to apply any of the properties, we want to make sure that our exponent and our log are single, meaning they are not being multiplied by anything, divided by anything, added, subtracted to anything. So we are going to first divide both sides by 5 so that we can get that 4 to the power x all by itself. So now I have a base of 4 on one side and a base of 7 over 5 on the other. I cannot make one look like the other, so we can either rewrite this as a log, or we can apply the natural log to both sides and then solve for x. Either way works. I'm going to show you both processes. So I'm going to first rewrite this as a log statement. So I'll have x equals the log base 4 of 7 over 5. So then x equals the natural log of 7 over 5 divided by the natural log of 4. If I would like, I could apply the natural log immediately to both sides. So I'd first get 4 to the power x by itself, then apply the natural log to both sides. So the natural log 7 or 5, then I will be able to move my power x to the front of my natural log, which then will allow me to solve for x by dividing both sides by the natural log of 4. Okay? Then I can substitute that into my calculator to find an approximated decimal value for my x. Okay. All right, so now that we have that practice, let's solve some more complex exponential equations. So here we have 7 to the power x minus 3 equals 2 to the power 2x plus 1. Okay, so I cannot make my base 7 look like my base 2 or my base 2 look like my base 7. So I'm going to apply the natural log to both sides. Okay. Now that I've applied the natural log to both sides, I'm going to move my powers to the factor location. So I'll have x minus 3 times the natural log of 7, and then 2x plus 1 times the natural log of 2. Okay. Now I'm going to distribute the natural logs to both terms within my parentheses. So I'm actually going to multiply. So I'll have x times the natural log of 7 minus 3 times the natural log of 7. And I'll do the same thing on the right-hand side. Okay. Now I want to move all the terms that contain an x on one side and all the terms that do not have an x on the other side. So I'll have x times the natural log of 7 minus 2x times the natural log of 2 equals 3 times the natural log of 7 plus the natural log of 2. Okay. Now that I have all of the terms that contain an x on one side, I can factor out an x. So x equals the natural log of 7 minus 2 times the natural log of 2. And the right-hand side stays the same. So to get x by itself, I can now divide both sides by the natural log of 7 minus 2 times the natural log of 2. And now I have an expression for the value of x, and I can substitute that, or enter that, into my calculator to get an approximated decimal value for x. Okay, but that's how you solve this exponential equation. All right, let's turn it up a little. We're going to solve an exponential equation that is quadratic in form. Alrighty. So here we have the equation 9 to the power x plus 3 to the power x minus 30 equals 0. Okay, so how is this quadratic in form? Okay, well, 9 to the power x is equal to 3 squared. So 9 is equal to 3 squared times x. We can also write it as 3 squared to the power x. Knowing that, I can rewrite 9x in my equation as 3x squared plus 3x minus 30 equals 0. Okay. Remember, quadratic is written in the form as ax squared plus bx plus c. Okay. So I'm going to let u equal 3 to the power x. If I let u equal 3 to the power x, then I can rewrite this equation as u squared plus u minus 30 equals u. And now I have an exponential equation that is written in quadratic form. This will allow me to factor, so I have u plus 6 times u minus 5. So I'll have u equals negative 6, and I'll have u equals 5. So now that I have my values of u, I need to determine then what value my values of x are for the original equation. So 3x equals negative 6, because remember u equals negative 6 and u equals 3x, so I just substituted that in. And when u equals 5, we're saying that 3 to the power x equals 5. Okay. Now 3 to the power x equals negative 6 has no solution since 3 to the x is greater than 0 for all x. Remember, that's a requirement. Now 3 to the x equals 5, we can apply the natural log to both sides of this exponential equation. Move the power to the front as a factor and divide both sides by the natural log of 3, okay, which then gives us a solution for x. Okay, so the part that's the trickiest when it comes to these type of problems is this first part up here, where you have to write your equation as a quadratic. So you'll have to identify the common expression that will allow you to rewrite these two terms with a common base. So one's 9 and one's 3, and I can rewrite 9 with a base of 3, which allowed me to rewrite it as 3 to the power x squared. Okay. All right. Solve logarithmic and exponential equations using a graphing utility. So the graphing techniques introduced to obtain exact solutions can be used to solve only certain types of logarithmic and exponential equations. Solutions for other types are generally studied in calculus using numerical methods. For such types, we can use a graphing utility to approximate the solution. So to do that, you are first going to enter the left side of the equation into y1, and then enter the right side of the equation into y2. Then you'll graph the equations and locate any intersection points. And the x coordinates of those intersection points would then be the solutions to your equation. So let's do an example. Here we're asked to solve x plus e to the power x equals 3. when we want to express the solution or solutions rounded to 2 decimal places. Okay. So in our calculator, let's pull up the calculator here. We are going to go to y equals. In y1, we're going to enter in the left side. So that would be x plus e to the x. On the right side, we'll enter that into y2, which is just 3. Enter. And so now let's graph both of these. And I see here that I have one intersection point. So I have a potential one solution. So we are now going to find the intersection between that. So we'll go second trace, and we want the intersect. So that's number 5. So we want our first curve, which is in blue here. And we want our second curve, which is the red. I just want to make sure it selects it. Now we want to guess where approximately that solution is or intersection is, which I believe it's here. It's the closest I can get. And that will allow the calculator to estimate for us the intersection point. So our solution then is going to be the x coordinate 0.79206. So that is going to be the intersection solution for our equation. So x equals 0.79206. Okay, so let's write that down. So x equals 0.79206. That is the solution to our equation. So as you are solving these equations, you can always check your solution by entering your equation into your graphing utility. All right, great. And that concludes section 4.6.